In this video, we're going to look at some properties of definite integrals. So the first property that we are going to look at is that the integral from b to a of f of x dx is the negative of the integral from a to b of f of x dx. Now let's think about why that might be. This integral we're trying to is to calculate the area under the curve f of x from x equals a to x equals b. Let's suppose we have some rectangle in here with endpoints c and d on the x-axis here to help us determine the width of that rectangle. Well, to calculate the integral, we take the limit as n goes to infinity of the summation from k equals 1 to n of f of x sub k star times delta x sub k, where this is some value in the kth rectangle. So we plug that into the function, we get the height of that rectangle. So some x value in the width there, right? In that interval from c to d. We plug that in, and we get the height of the rectangle. And this right here, this width, this is meant to be the width of the kth rectangle. So that's just d minus c here is our width. Okay. So what does this mean, right? So let's go ahead and write that down. But delta x sub k is d minus c if we integrate from x equals a to x equals b. But delta x sub k is c minus d if we integrate from b to a. Right? If we are going the other direction here, now our second value is c, and we subtract away the first value here if we're traveling from this direction. And so when we do this calculation, that interval, the width of the rectangle, is going to end up becoming a negative of what it was before if we integrate the other direction. The height is going to be the same thing. So each of these terms, if we integrate the other direction, is just going to be the negative of from the forward direction, which tells us that the sum is just going to be the negative of the original sum. And that's exactly what this property says. That if we change our order of integration, then we just take the negative of our integral. So if we had just a to b and we change that to b to a, we need to multiply by a negative 1. All right. Let's look at several more. Well, what about the integral from a to a of f of x dx? What is this? Well, this is the width here of our region that we're trying to find the area of. Well, here we go from a to a, so that means there's no width. If there's no width, that means the area is 0. All right, let's look at our third property. If we take the integral from a to b of some constant k times f of x dx, this is just k times the integral from a to b of f of x dx. So we have a constant multiple rule, where if k is a constant, we can just factor out that constant. All right, our fourth property here is, actually we need to write something first. Assuming f and g are integrable functions, then property 4 is the integral from a to b of f of x plus or minus g of x dx is just the integral from a to b of f of x dx plus or minus the integral from a to b of g of x dx. And in particular, of course, if this is a positive in between, then it's a positive over here. If we were subtracting here, then we're subtracting over here. Our fifth property that we want to discuss is that the integral from a to b of f of x dx plus the integral from c to d of this same function, it's got to be the same function here, sorry, not c to d, b to c, sorry about that. This is the same function, and this integral ends at this place that the next integral picks up. What is that? That is just the integral from a to c, then, of f of x dx. And let's draw a picture to see why that is. If we have a, b, c here, then the first thing here, the integral from a to b of f of x dx is this region. The integral from b to c of f of x dx is this region. And then if you add those two up, clearly that is just the total area under the curve f of x from a to c. So we don't really go through and prove this right now, but we see from the picture that this should absolutely be true. And it is. All right, still several more things we want to write down. Let's do property 6 here of definite integrals. If f has a minimum value, which we're going to label as min of f, and a maximum value, max of f, on the integral a to b, then min of f times b minus a is equal or less than the integral from a to b of f of x dx is equal or less than the max of f times b minus a. Sorry, that was off screen. Let's draw the picture to see why that is. All right, if we have some function here, and we take the integral from x equals a to x equals b, the b minus a times min of f is just the area of this rectangle right here. The minimum value of f on that interval, and which is the height of that rectangle, times the width of that rectangle, gives us the area of that rectangle. And then if we go to the maximum value of f on that interval a to b, then we find that area of the rectangle. And what we see is that the area of the integral here, so the area under the curve, in other words, the value of the definite integral, is between those two values. And that's exactly what this inequality says. All right, let's move on to part 7. And that is that if f of x is equal or greater than g of x on the interval a to b, then the integral from a to b of f of x dx is equal or greater than the integral from a to b of g of x dx. Draw a quick picture of this. Right, if we have some f of x up here and g of x is equal or less than that, it might touch it at some point on that interval, then clearly the area under the curve g of x is less than the area under the curve of f of x, or equal or less than if they happen to be equal at all points. Okay, now, all of the things that we've said are true. We've been talking about areas under the curve so far, but really all of this is true if the function is negative on some intervals. But we can no longer think of it as area under the curve. Or maybe we can think of it that way, sort of, but it's not really that, unless we think of negative areas under the curve. So let's draw a picture. If we had from x equals a to x equals b, and the function dipped below the x-axis at some portion on that interval, what the definite integral does, the integral from a to b of f of x dx, is we have this area here, A1, which is this region below the f of x, above x-axis from x equals a to whatever this is, whatever point this is. And then we have some a sub 2 here, which is the area below the x-axis and above the curve now. And then we have a sub 3 here, which is this region in here, the area of that region in there. A sub 3. Well, this integral, this definite integral then from x equals a to x equals b is actually a1, where that area is positive, minus a2, where we subtract off the area of this region, plus a sub 3, because again a sub 3 is above the x-axis, so this region is positive. So when we integrate something like this, if we just calculate the integral, you will end up with something that is equivalent to a1 minus a2 plus a3 if the function looked like this on that interval from x equals a to b. All right, we have one last thing we're going to write down for this video, and that is that if f is integrable on the interval, closed interval a to b, then its average value on the closed interval a to b, also called its mean, is, and that is AV of f, so average of f, is 1 over b minus a times the integral from a to b of f of x dx. And this makes sense. Why does this make sense? Well, this right here is the height of the rectangle. Sorry, I should clarify that. This right here, let's do this, is the area of the curve. Area under the curve from x equals a to x equals b. All right. And then we can, what's the width of our region? Well, that's from b to minus a, that is b minus a. So if we divide by the width, we're going to get an average height. So that's what we've done here. So b minus a is the width of the interval. And if we transformed this area into the same area but in the shape of a rectangle, and we take the total area and we divide by the width, then what we get out is the height. So as I was writing here earlier, this whole thing together is the height of the rectangle of width b minus a that has the same area as the integral. As the integral from a to b. And what does that do? Again, that just gives us an average value over the interval from a to b of the function f of x. Let's think about what that means, right? Usually when we talk about averages, we're taking an average of a finite number of discrete points, right? What do? We add up all of those points and then we divide by the number of values. Well, here what we do is we add up the heights, a bunch of heights, really areas of rectangles here. But we can almost think of it as adding up a bunch of heights here and then finding out what all of that is, dividing by then the width of the interval that we're adding up all of these heights or really areas on, and that gives us an average height or an average value. And that's it for this video.